makes MBX what we're putting this program on. We've been doing an incredibly great job over the years, and this kind of material, this kind of program is just really, really crucial to your own development and keep some of your sanity as well. Although I've been in academia for the last 20-some or so years, my first 22 years was in hospitals doing biomedical in the trenches. And although I enjoyed the teaching, my first love, first passion is hospital biomedical. Every time to this day I go to a hospital, I get that longing to be in that place. As difficult as it was, the sight, sound, the smell, the knowing the good that's going on. I don't think there's going to be anything more noble, profession that we could be doing what you guys do. But what I want to do today is challenge some thinking that has been going on since the birth of our profession. It started maybe late 60s, early 70s, measuring leakage currents. And what I hope we're going to be able to do what the heck? John, run out, you think? Oh, I think I know what it is. I just we gotta get going to a different part here. Look at that, huh? Yeah, I don't know if anybody's got, if John's out there, there's like something's locked up here. Anybody have any luck maybe finding John? You did? Okay, thanks.
Trying to do.
Need help? Yeah, it's locked up. But
I'm just a tech. We're all
yeah.
biomeds.
Yeah.
What, the PC's locked up? Or you're?
Well, this is working now. It's just not projecting. So if we got
Your expand the it's coming out through an HDMI cable, right?
let's see what the settings maybe.
To two. Do I expand it to the expand the screen?
Yeah, that's one if I can get down there.
There you go. You're live now.
Yeah,
There you go.
okay. Well, we gotta get rid of the,
Yeah, I figured I'd get here and you have it, by the time I got it.
yeah, it's, I just can't get out into the presentation mode. I swapped the remote out, thinking it might have been the remote.
Well, sometimes it,
Oh, there we go.
that working for you?
Yeah,
All
we
right,
can get that
get this off. the-
panel.
Okay. Does that work?
Yeah. that works. Yeah.
No, it's not working? Yeah, I think it's,
There we go.
okay. I'm walking away.
Okay, thanks, John. Thanks, you guys who've been there before. And what I basically want to do at the risk of blasphemy is challenge our 50-year-old history of measuring leakage currents. And but hopefully by the time we're done here, we'll see that this is a task that might again have to do some pushing on that we can safely get rid of doing in our hospital and medical devices. One of the things that's crucial, though, I have to ask you to temporarily at least try to suspend, decouple leakage current measurements with safety, patient safety. Not talking about compromising patient safety at all, but going to be challenging our 50 years of measuring these leakage currents and why we can get rid of doing that. Okay? In order to do that, though, what we have to do is review some old fundamentals, some AC fundamentals, of course, topics that you may have had a long time ago in your education. How these leakage currents, where they come from, and what they're really all about, some of the physiological effects of the potential that they can have on the body, and then how all of this stuff got started in the 70s and even goes beyond the raw data type stuff. And then hopefully see by the time we're done why we can safely, legitimately stop doing these tests. All of this stuff, again, is gonna might be a little bit stretched going back to some of your fundamentals again, but it all starts out with Faraday's law. Basically, all he ultimately came up with is that if you have a moving coil in a magnetic field, you can generate a voltage across that coil, across the terminals of that coil. And that's precisely how we generate alternating currents since this time. It's just the number of turns in the coil, moving the coil in a magnetic field is what generates the sine wave. And if this little video works here. Let's see if we can. I want to turn that. Bottom line is, it's that rotating coil creates the voltage. Okay, and that ultimately what creates our classic sine wave. As that coil is moving through that field, our voltage alternately goes from 0 to a peak positive to a peak negative, back down to 0. And the period or the frequency of that signal is dependent on the speed of the turbine. So that the power plants, these turbines are spinning at 3,600 RPM, and that's what exactly creates our 60 hertz power that we have in this country. The reciprocal of the frequency gives us the period. So the period of this waveform, the time it takes to go to one cycle is 16 milliseconds. If you just kind of bear with me for a few minutes while we get through some of these fundamentals, you'll see how all of these fundamentals are basically that there's a foundation for the whole concept and topic. Okay. Remember the old days for some of you guys who use the oscilloscope? I don't think we even use them anymore. The old oscilloscopes allow us to look at these signals because we can adjust the horizontal time base. In this case, it's set for 50 microseconds per division vertical division is set at 0.1 volts per division, and we can characterize and measure signals using this technology. And when we do that in this way, we can see we can measure the period. We've got 4 divisions, 4 times 50, 200 microseconds. So the frequency of this signal, 1 divided by 200 microseconds, is about 5 kilohertz. The frequency, the peak amplitude there, 0.2 volts. So in your memory, maybe you've seen some of this stuff, and kind of make your feelings fall out. Some of you might be even having a post-traumatic stress response, but don't get into the wow. Yeah, we'll talk about it. But anyway, it's just a mathematical way of describing the voltage at any point along that sine wave. Stuff that you can do every day on the job. No, we don't. But we have some very precise ways in which we can describe these waveforms. And fortunately, we've got a shorthand technique that is practical that we do use all the time. And that's what we refer to as the RMS value of the sinusoidal signal. And that's what we're going to be using. That's what all of our instruments use. Your AC multimeters are RMS reading meters. So when you plug that meter into a wall outlet, what you're reading is 120 volts RMS mean squared. It's a shortcut method, and all the RMS value is an equivalent voltage that creates the same heating effect as an equivalent amount of DC. So if we have a water bath here with a thermometer, and we close the switch and we have 120 volts of DC, we get some heating effect here, a certain amount of heating effect from 120 volts DC. We get the same heating effect with 120 volts RMS alternating signal. Sometimes it's also called the effective value, because it's effectively the same thing as DC. Okay, and so what the RMS value is essentially a DC equivalent signal. So of our alternating sine wave here, the RMS value, if we know the peak value, we can just multiply it times 0.707, that will give us the RMS value, and then conversely, if we have the RMS times 1.414, we can find the peak. So what that translates to, in reality, sinusoidally, or mathematically, our 120 volts RMS is really a sine wave having this characteristic 170 volts peak, and the frequency here 377 radians. So if we divide 377 by 2 pi, you get 60 hertz. So this 170, where this has practical implications, if you're replacing diodes, capacitors, and power supplies, these peak values here are what your diodes have to withstand, your capacitor working voltages have to withstand. So this is where we have to be mindful of it for practical purposes. We don't live in this. We live in the RMS. We'll see our RMS microwaves, that becomes significant a little bit. But anyway, any alternating waveform, we can take an RMS value from. So when we get that term, we mathematically will square it. So when you square an alternating waveform, it kind of gets rid of the negative going forward. Squaring the negative is positive. So all the negative going stuff is made positive. We take the average of it, take the square root again to get back to our original units. The artificial limbs that are really controlled prosthetics that are controlled from our EMG muscle off of our skin. We take our raw EMG, we are taking RMS value, and now we have essentially a DC signal coming from our muscles that we can use to operate actuators. Okay, couple of key concepts also. Once we have this alternating signal, this alternating power, how do we get it to our buildings, our houses, our facilities? And we typically we transmit power at very high voltages. Much more efficient to do that than transmitting at lower voltages. Back in the late 1800s, DC may have read about the conflict going on between Edison and Westinghouse. There was a real professional pissing contest going on between those two guys. Westinghouse was promoting DC for power throughout the country. Edison had a bunch of patents on DC motors and things, so he was promoting DC. And they were doing this classic media kinds of stuff. The electric chair had just come out using AC. So they were using that to scare everybody. Fortunately, AC went off, and it just makes the most sense. But we have a key element there, the transformer, steps, this is just in our residential environment now, steps down to typically 14,000 volts kV, that power is being transmitted at, steps it down like a transformer to 240 and to 120.
This is just, if this one works, we'll see. They have to deal with this alternating as well as the stimulus alternating. That induces a voltage in the secondary. So that's how you simply depending on the number of turns in the coil, we can step up or step down voltages and currents. In your operating rooms or cabinets, we still have isolated power. If you still have environments that have isolated power, the turns are the same. So we can put in 120 volts in, we get 100. Isolation comes in is that now the neutral here we'll see on the secondary, this is the second, it's no longer a reference to physical. We'll see some of the significance of that again as well. Power in ideally equals the power out. This is precisely why the transformers get warm. The wall works, the things that you've got plugged into the wall, why those get warm is because we're putting in more power than we get out. And they can be pretty efficient. They can be 80-90% efficient, but that 10% or so benefits is heat loss inside the transformer. This is a crucial concept. Again, some of this stuff is probably done for you. You've already gotten down. You just have to bear with me a little bit. But what's so crucial here, the way that our power is distributed, not only residentially, but in our commercial buildings as well, hospitals as well, is right where the power enters the building, the neutral is connected to the ground. The ground and neutral are bonded right where the power comes into the facility, and that is also then literally connected to the physical dirt of the earth. And that's what makes our power, our available power, our outlets, reference to the physical earth. So that small plate on the receptacle there, the hot side, is 120 volts RMS above ground, above earth. So literally, if you're up naked standing in a mud column, you stick your finger in that little hole, you're gonna die. That's reference to the physical earth. Any current flowing in the ground wire at all. All the current that's powering the device leaves the hot, returns via the neutral under normal conditions. But this is the crucial concept right there. The classically grounded receptacle, and I don't know if you ever knew this, I didn't know this until about 5 years ago, a student at my school in 1928 invented this thing. The conventional grounded out. And the wise tale in the area is that he was living in an apartment building. His landlord's cat kept getting shot in the back of a big box fan he had. So he came up with this idea of adding an additional ground pin to the case of the fan. The cat didn't get shot. Can't imagine what kind of royalties if the guy got a penny for every outlet. I mean, I don't know whatever happened to him, but that's the configuration of the outlet. And this is the stuff that we've been doing since the beginning of time. What we continue to do, and this is a good thing to do. So I'm not in any way suggesting you stop doing this. The ground core continuity test, what you do with your safety analyzers, if you can find a ground point on the machine. What we want to continually verify that ground pin is indeed electrically only connected to the case of the device if you have a conductive case. So this is what we've been faithfully measuring since the beginning of our time. When you think about the effectiveness of the ground, in order for the ground to be effective at all, this also has to have good ohmic conductivity to the physical dirt. And what that means, you could have a great, you could have your 0.5 meters or so from the pin to the machine, but there's also going to be resistance between the pin and your sloppy outlets. You can always see this if your plugs get warm. You've got a high resistance and normal between hot and neutral, if you're getting power loss. Power, remember, is I squared R. Square of the current times R. So if you have a 10 amp device and say a ground resistance between the pin here and the receptacle of 1 ohm, 10 squared times, when you have
100 watts of power being dissipated right at that interface. So this is something that we kind of often just shut down the facility and say, well, that's the facility's thing. But this is one of the reasons the hospital is such a good thing, because of this contacts inside of the bubbles are much more robust. But this, in order to be effective, that ground pin also has to be ohmically connected to the physical. Anything that interrupts that pathway makes the ground pin a useless thing. It's not going to do its job. There's two reasons why we have that. See in a minute. And again, outside your buildings, you're outside your homes, you can't see it anymore. It's all very, it's typically going to be 1 or 2 10-foot blocks. Very physical dirt. That's brought into your circuit panel, and that's where the neutral ground bond occurs at that point. I don't know if you've ever had to do this, but it wasn't uncommon at all. You have weird lockups and weird problems every now and then. You can't quite get your handle on. A number of things I used to do is that I just had a simple pigtail, neutral ground voltage. You ever done any of that when you're troubleshooting? You might just think about that sometimes. If you're encountering devices that are kind of behaving flaky, and you can't figure out what's going on, just get a power plug, just connect the neutral and the ground to your multimeter. Measure that voltage. Typically, that voltage ideally should be very, very close to 0. And if it starts to get less, if it's less than 2 volts or so, it's probably kind of okay. But if that voltage starts to get too high, that implies that you've got connection problems. That can create very stable funky behavior in some devices. You don't want to cut that pin off. We don't have to do that, right? But you need somebody that probably did. You don't have to wire outlets. You don't want to cut that pin off. A couple other key concepts. You've heard of these guys too, Ohm's law and Kirchhoff. They've got some fundamental laws that dictate how these currents and voltages behave. And law, they're not up to debate. They're in stone, and that's one of the beauties of this material, is that it doesn't get obsolete like Java or C++, or a lot of that software stuff that mutates every 6 months. These things aren't going in stone. They're repeatable, stable relationships, like they call them laws. And Ohm's law fundamentally dictates the relationship between voltages and currents in circuits, both DC as well as AC. And we're primarily concerned with what's going on in AC devices. Everything we plug into a wall outlet is an AC line operated appliance. And everything that we plug in to the outlet has an impedance associated with it. Okay, and that impedance can be one of 3 forms. It can be purely resistive, like a baseboard heater, incandescent light bulb, looks just like a resistor to the wall outlet. It can look like a resistor and a capacitor, or it can look like a resistor and a conductor. Motors, solenoid valves look like an RL to the power. So from the perspective of the electrical outlet, whatever we plug into the outlet is to see one of these. I don't care what the device is. Hopefully we can show that it looks like one of those 3. Okay. So you can just think of impedance if you don't haven't already think of it as kind of like an AC dependent resistance. Okay, so the capacitors will change their impedance depending on the frequency. Inductors change their impedance depending on the frequency. Resistors just stay the same. They're not affected typically by frequencies. So if we had a pure resistor, coffee pot, hair dryers, light bulbs, incandescent light bulbs, just looks like a resistor. But in the law that Ohm's law applies here. So if we had, a 100 ohm resistance, incandescent light bulb plugged into a 120 volt RMS outlet, the current would be V over R. 120 over 100, 1.2 amps would be full. And the other key thing when that happens in those types of circuits, current and the voltage are moving in phase with each other. So if our line voltage is 120, the current is going to be exactly in phase with that voltage. And this ultimately becomes significant shortly as well. If we have an RL circuit, equivalent load. So you get inductors, motors, loudspeakers. They look like a resistor and an inductor in series. We can look at it in parallel as well, but you can think of it just for simplicity, it's in series. So the outlet doesn't know the difference. So vacuum cleaner or motor currents maybe be different. The key thing with these kinds of circuits, however, is that the current is going to lag behind voltage. Fundamental behavior, the currents in inductors cannot change instantaneously, so there's always going to be a bit of a lag. So just by where I'm going with this, just by looking at these waveforms, we can ultimately determine what's causing it. Is it an RL circuit, or is it an RC circuit, or is it a purely resistant circuit? We'll see how we're going to do that in a bit. Capacitors, capacitance, this is another passive component. Any time we simply have two conductive surfaces separated by an insulator, bottom line, that's all a capacitor is. Two plates, two conductors separated by an insulator. They can be a physical capacitor, they can be virtual capacitors. There's capacitive coupling right now as we're sitting here in this room between top of my ball head and power line, but there's capacitance there. And that capacitance is what contributes to some of the noise in some of our sensitive measuring environments. But anytime we've got two conductors separated by an insulator, we have capacitance. This is going to be crucial here in a bit. That capacitance has a impedance to it that we call reactance or X of C. And the key thing with capacitors, the amount of that resistance, if you will, the impedance, is inversely proportional to frequency. So at real high frequencies, that reactance goes down. Did you ever have dental surgery, or maybe in some of your hospitals, you got hypercators, you've seen those? They're like little miniature ESUs. The dermatology people use them, dentists use them. It's just a probe. You sit in the chair, and there's no ground wire at the bottom. The practitioner just has a probe, and they can do electrosurgical work in your mouth, skin, with no return electron. Why that works is that your body is completing the circuit capacitively coupled to the chair, the ground, and those small currents. They get a much smaller currents than here. So because the frequency of those hypercators, the ESUs, is so much higher, you end up getting a very good electrical connection just to capacitive couple, not a physical wire. Okay, with this capacitance, and specifically we call it straight or parasitic capacitance in our devices, is what gives rise to our leakage. This is where it comes from. The sheer proximity of conductors in our devices creates capacitance. We call it, sometimes we get straight or virtual capacitance. It's not a physical capacitor. It's just two wires next to each other. Insulated wires. We have capacitance here, which will have a reactance at 60 hertz, which will permit currents to flow. So the currents will flow from hot side to neutral, or in this case, the ground. This is a metal case, and if it's grounded, we've got capacitance between the hot side of the line in the case, neutral in the case, even in a line cord, unterminated line cord. You measure the capacitance, unterminated line cord, say between hot, neutral, hot ground, you get somewhere in the 10 nanometers, just from a line cord. Nothing connected. And so one of the two reasons we have grounds on these machines is to drain that leakage current away. It's been called touch currents now. I never really liked that term. I like the leakage. I think of a tire with a small pinhole in it. It's a sheer byproduct of anything we plug into the wall. And it's leaking effectively out of the device if and only if we provide one of the reasons we have that ground wire on devices like that. I don't know if some of you guys remember, like the stuff's still around anymore, but the old blue line cords, Dale, the manufacturer, used to make these really thick, big, long line cords. They're blue, and they're pink, they're thick, and they had much lower leakage current associated with them because they have these polypropylene fillers in here to separate the distance of the conductors. So it had much lower leakage current, whether it was a bitch to work with. You're getting the plug capsules bad, straight leads are different. It's a big, bulky type of cord, but had a lower leakage current. we kind of knew what was going on. But the goal was to try to minimize the stray available leakage currents. Okay. So again, where I'm going here, these capacitors, and these can actually be a physical capacitor. Probably had an occasion where you're measuring the leakage on devices, you make it way over 500 microamps. Any device that has built-in line frequency filters in it have physical capacitors to ground inside there. So it's not a virtual capacitor, but it's a physical capacitor. And what those devices do, obviously they filter high frequency noise and garbage that's coming into the device, shunting it to ground. It also protects the power line from crap being generated in the machine from getting out of the power line. So we could have intentional capacitors there. The primary difference here in terms of these concepts is now the current is leading the voltage in RC equivalent circuits. And this is the point of this will be apparent here what we coming up. Okay. So just for example, we had 10 nanofarads of straight capacity, 10 to the minus 9, 10 billions of a farad, small amount of capacitance between the hot side and the case. That 10 nanofarad capacitor looks like a 265 kilo resistor. So if you put a 265 kilo resistor between the hot side of the line and ground, you're going to create a leakage current here of 452 microamps. That's what you would literally be able to measure with your safety analyzers if you plug this device in with that kind of straight capacitance. You can replicate this using the physical capacitor too, and you get the same thing. Okay, because now real capacity is just the sheer proximity of conductors. Then you got hot conductors physically next to a case, and this is inversely proportional to the distance between the conductors. So the farther away we have less capacity, the closer in contact with the case we have more capacitance. So there's nothing wrong with the circuit. It's just the inherent way in which it was designed and been built. And you can measure this, and look where you get this old Valleylab ESU there, and we measured its leakage current with a analyzer. You get about 81 microamps. You can also run it on an oscilloscope and look at the leakage current across the standard 80 kind of load. So that's the small waveform here, and our 120 volts going in. So if you look at those two signals, and from these signals, you can show, again, this is not an opinion. I didn't invent this stuff. It's just how it is, how it works. That it looks like we have an equivalent capacity of 1.8 nanofarads in series with 155 kilo resistor. So from the perspective of your safety analyzer, you're measuring the leakage current on any devices. This is what it looks like. In other words, your leakage current analyzer doesn't know it's looking at an ESU, vacuum cleaner, a pump. It doesn't see that. It's measuring the current, and that current is coming from an equivalent, in this case, of that combination of R and C. That's what's giving rise to that leakage current. That is ultimately what's going to create the coupling or the source of our leakage current, is this equivalent circuit inside the machine. So you may have seen this, the standard AMI anti-load. For the first 10 years or more of our existence, we were just chasing leakage currents. You know, many of the programs we had, they didn't give a shit, care of the fibrillator work, but no leakage current stuff. You know, we were measuring that stuff, tracking it, writing it all down. We just were crazy about leakage currents. And just because our knowledge wasn't quite where it is today. This is how we simply measure it. When you plug your device into the analyzer, you're essentially inserting a standard load, which at 60 hertz, it looks like a 1 kilo resistor. We're simply inserting that load in series with the ground. And then we're measuring the voltage, the RMS voltage across that resistor. millivolts, RMS millivoltmeter divided by 1 k ohm gives us current in microamperes. So that's all we're doing with the safety analyzers. Okay? How does that come back? Some of that stuff coming back? Where that source of the leakage currents come from? That's kind of crucial going forward here, where it comes from. And ultimately, where we're going to go, before that leakage current can do any hammer, we have to get it to the wrong place. Once we shock anybody. Okay? So the other thing we then need to appreciate is what physiological effects does electricity have on the body. Then you probably know it's the current that does the damage, that does the shock, that does the potential damage. You can get high voltage static charges, can be in the tens of thousands of volts. If you startle, you're not going to die. So it's the magnitude of the currents, and electricity has one of these three effects, like the tasers. They put the body into a massive state of tetany by stimulating all of the muscle between the two darts when they hit you. You can have in other situations, even in electrocutions, you get resistive heating, temperatures in the brain hours after execution, the brain can call it on to some degree, it just kind of cooks you to death. Okay, this is an old classic example. It's been in your textbooks forever. It's a little bit off. We just use these different levels to describe how the body responds to electrical currents. And at the lowest level down here is what we call a threshold of perception. And the actual threshold of perception is much lower than this, and we'll see in a minute. The smallest amount of current we can just barely detect is that threshold. If we move up a little bit, actually the more current numbers are detected. And this is right around 7 to 9 milliamps AC. You have that pass through your arm, you physically will not be able to let go. So much tetany going on in your arm finger flexors that you cannot let go of the conductor. That is precisely why our ground fault circuit interrupters are designed to trip around 5 milliamps. We want that to trip before we hit that electrical threshold. And if we go higher in currents, you have the linemen working on high voltage power lines, they get 10 amps, so there's the shoes off their boots off their feet. But anyway, a long time ago, I made this device. I was trying to talk to students about leakage currents, microamps. They're looking at you like, where's clue? You know, microamp had no concept of what that even meant. So I made a device that you could literally put your 2 fingers on it and turn the knob. You'll get your whole threshold of perception. Put your 2 fingers on the electrodes, you turn that little knob, and that current that's now passing between your fingers, right when you begin to feel it's not tingle. So, of course, I'm not doing that any less, but is how you feel appreciated. I get the feeling. And anyway, what happens when you first feel that tingle is that you have stimulated receptors in your fingers, physiological receptors. You've exceeded the threshold on those nerve action potentials. The only way for the brain that's going to feel anything is that you have to get the voltage across the cell membrane greater than this negative 50 millivolts or so. I feel kind of like a cellular orgasm. Once that nerve hits that threshold, it's going to fire. And once you hit the threshold, nothing happens. So you can have currents passing through your fingers and you don't feel it. And why you don't feel it is because it's below your threshold perception. Same thing with sound pressure level hearing test. You can have tones going into your ear, but if it's below threshold, you can hear it. So make a little device to help students appreciate that. And I used to give it to a number of students. We'll see a bit of these nerves that you kind of think in the form of transducers. They literally, we have them throughout our whole body that are sensitive to light, their eye, hearing, force. We have shear force sensors in our fingers that can count forces, temperature, electrical. We have a whole host of these different transducers. And the way the body encodes stimuli is through frequency. The amplitude stays fixed. So when this nerve fires, it fires up to about 20 millivolts. So literally the voltage measured across the cell membrane, we can actually measure this, flips, depolarizes as it's called, and it peaks out about 20 millivolts. Okay. And that's regardless of the intensity of the stimuli. The more intense the stimuli, brain encodes that from frequency. So the neuron just fires fast. So if you just lightly step on a tap, brain goes, bing, bing, bing. Whereas if you really nail it, you shit, that hurts. So the brain interprets intensity by the frequency. This is getting significant. It's all coming together. Anyway, I use this little box, and we have high school kids coming in during the summer, a lot of times, these summer programs. So I force them to determine their electrical threshold of perception. And we also did some freshman classes too here for a group of females. There's about 240 microns. They can just barely feel. The guy right around 250, a little bit higher. Okay, statistically, this isn't significant. And we see that this is error, as they call it. So this is plus or minus 2 standard deviations. So 95% of this class had thresholds between these two. So the guys see how it's much higher. I don't exactly know, but I'm almost convinced that it's this macho thing going on. You have guy here. I don't feel about it. The girls pay attention. They always talk to the girls like, where are you going? So I suspect that's why that greater variability was there. But anyway, the point is, this is what you could just barely feel. This is getting significant as we go on. You may have heard of this. Ralph Nader, he's often sometimes credited with giving birth to our profession. The very first job I had in 75 was starting a biomedical department because of the Joint Commission at the time and our fear over all this leakage. And so he's often credited with starting this by claiming 1,200 accidents per year were happening in the hospitals. Never, ever, ever, ever was shown to be true. And actually, he was one of the first ones to do it. We really didn't want to blame anybody. We all blamed this physician, Carl Walter, who about 68, he's the one that first came up with it. And he was a really well-respected dude. I think he may have been a surgeon, Watson. He was credited with developing and inventing the blood bags for blood. He also played a big role in the sterilization industry as well. He was on NFPA committees. So he was a really respected, well-regarded physician. He came out and said we're killing all of these people, again, based on very, very thin evidence. Ralph Nader ultimately picked it up. Just repeated it. I don't know if you remember Dr. Joe Noble, he used to be the first president of PCRI. He's the one early on came out and said this was all kind of bullshit, that we're just scaring everybody. So everybody's going to go out and buy isolation transformers and all this safety stuff. And he was basically saying there was a lot of phony statistics used to manipulate, mobilize the industry in a way that it didn't really need to go. Malcolm Ridgway, Dr. Ridgway, one of the first clinical engineering handbooks, he's got an incredible detailed history, whole thing going on. Okay, but this is how it all got started. This scenario was the classic worst case scenario that we used to teach, try to get our attention, scare the crap out of us. And the nature of that scenario is you've got a patient with an involved catheter into the heart, connected to an external pacemaker. So you got a direct electrical connection to the heart coming outside into a box. Okay, they're laying in an electrically operated bed. It just happens to have a bad ground wire, which would not be at all uncommon. Plug, wire, outlet, anything that would prevent the leakage current from being safely drained away bad. Patients also connected up to an electrocardiograph, and at the time in the day, the right leg in the older machine was actually grounded, or very close to earth. So we would intentionally ground patients back in those old days. So you got a electrically operated bed, metal guardrails, the unsuspecting nurse attendant leaning on the guardrail, putting it around with the catheter coming out of the patient's heart, doing what? Providing a pathway for leakage currents from the bed, because the bed's not grounded. The available leakage current on that bed now has a path to go from the bed through the nurse, below threshold perception, can't feel it, doesn't even look at it, plays around with the lead wires, leakage current now passes right through the car, return path, Yeah, we killed the fish. And this was the scenario that was published, 71, and used all over the place, and that's what scared the shit out of me. Got it wrong. Yes, all. You know, and at the time, it seemed kind of, yes, that could kind of maybe happen, you know, so our thought was if we can control the leakage currents, we can control potential hazard. I don't know, some of you guys were around later in the 70s, or it was stupid. Dumb half NFP requirement that we remember the equal potential rocking system. If you guys remember that, some of the older hospitals, you see these big plates and they have all these big jacks. You had all these, there used to be a NFP requirement, you had to have all these redundant grounds. Patient was number 10 being ground wires, floor frames, everything. Theoretically, everything's grounded, you can't get shot. You're going to trip and break your neck if you're falling over. You can't afford it. You won't get wet. Fortunately, that wasn't. That was the scenario. And all we also knew at the time is that we could fibrillate dog heart with maybe 50 to 400 microns. So if we're way below, if, you know, we're now in this hundreds of microamp range, we're killing dogs at 50 microamps. That's the original requirements is to be much lower, around hundreds. So we just didn't know at the time. This was the research that was driving the fear. Okay, but anyway, what we've got next here, we're going to see are the necessary events. There's 5 things that have to happen. Anybody's going to get shot. 5 things that have to happen. Okay, first of all, what you have to have is a conductive surface on the device capable of being energized. So you got to have some kind of conductive surface that can get energized within. The struggle you may have today is to finding devices with conductive surface. We got many devices that conductive surfaces. There might be a ground pin on the back. They give you just a ground resistance check. There's nothing conductive on the surface of these machines, even our beds, that can be energized from the inside. First thing you got to have rear shock. Okay, yep. You talk about coupling. There has to be sufficient coupling between the passive line and that case. So there has to be, you know, sufficient capacitance, resistance before you have any meaningful amount of leakage current available to that case. Second thing. The third thing, so the magnitude of that leakage current is determined by that impedance here, this virtual impedance inside the machine. Okay, third thing we need is a defective ground. So either the ground wire can be bad, the plug can be bad, the ohmic resistance between the plug and receptacle can be bad, ground. Third thing that has to. Okay. So, and this remains a good, viable thing to do. You've probably all seen ground resistance is getting too high. If you've got a good intact ground, it doesn't matter what the leakage current is. If you've got devices that are semi-permanent, they don't move around, if you're really worried about it, you put a redundant ground on the device, protecting you even further. But that resistance, that's reasonably low. It doesn't matter if the leakage currents are because they're going to drain away. And why we can drain away is from one of the fundamental laws of Kirchhoff's current law. And all that says is that the current entering a node here, the currents leaving the node have to equal the currents entering the node. And ultimately, what this tells us is this is where we get our protection from the ground. If I have low resistance ground, say a half an ohm, versus say 1,000 ohms for a full person patient, and I'm a leakage current, 500 microamperes, I'm going to take the path of least resistance to ground. I'm going to divide. Some of it's going to go, most of it's going to go to the low resistance wire ground, 499 of it. The patient's going to get 1 micro. So he's going to die. 25 feet. And this is why the ground on those devices is so crucial because of Kirchhoff's current law and the protective effect we get from having that low, very, very low resistance ground. And the fourth thing we have to have is some reasonably good contact between the case and the patient person. This can could be a deliberate electrical connection, or lead wire, whatever, but it needs to be a good low impedance contact between the patient and the case. Fifth, lastly, we need to ground that patient, complete the circuit. It needs to be a low impedance pathway from that patient to the physical ground. And if all five of those things are in play, then are we going to get that leakage current up there, potentially flowing through to a person, patient? That kind of thing. Five things that have to happen. In another paper I found that even if all those things did occur, even if you're having, arm to foot, there's still only estimates of about 10%. The studies that they did, only about 10% of that current's going to go through. Because you've got all this other tissue shoving around the heart, low impedance pathways to vessels, nerves around the heart. And even though under that worst case scenario, relatively small amounts of current. Five things you got to have. Remember your latch gates and input or gates and we're going to get in this case we have 5 inputs. Every one of those 5 inputs has to be high. Has to be present. 1 plus 2 plus 3, they all have to be present. And then we'll get either a micro or macro shock. All 5 of those have to be present. Okay. Now what are the chances of that happening? This is where it becomes bottom line. What are the chances of all 5 of those? These are called a compound probability. All 5 of them, we don't know what they are. It doesn't matter. But probabilities are physical numbers between 0 and 1. The probability of 0 simply isn't going to happen. On the other hand, if you got a probability of 1, absolutely will happen. Flipping a coin, even chance about 50-50. Probability of about 0.5. Every one of those events, those 5 events, has a probability associated. We don't even need to know it, but every one of them has a probability associated with it. What happens when we have independent events like this, the probability gets smaller and smaller depending on the events we have. So if you flip one coin, you get a 50-50 chance of getting a heads. If you flipped it twice, the chance of getting 2 heads is 0.5 every 1 time. Similarly, it will get smaller. Anytime you multiply a small number by a smaller number, it gets smaller. It just keeps getting smaller and smaller and smaller. So the bottom line here, the chance, if you reduce any one of those 5 things to 0, whole chance of shock goes to 0. You got an inductive case, no external metal, capable of being energized inside, not double insulated devices. There's nothing you're going to get a shock from that device. If you don't have any contact between the patient or some worker between the device and the ground, any one of these goes to ground, the whole thing. And then you put all of that together, and this is where we kind of end up. Still definitely got to do, how the line works, you get the ground, where you get the ground shredded, casket, unbent. Clearly got to keep doing it. There's nothing, that is a legitimate component of safety. Verifying the intent, mechanical integrity of the line cord cap string leaves ground cord resistance. Another great thing to be verifying, because if there is a leakage current, if there's anything issue at all, it's going to be going off the ground. The ground is also very helpful in controlling and minimizing some of the electromagnetic radiation that's being generated inside the device itself too. So there's some other benefits from having an intact ground. That makes sense. Just to be conscious, be aware that there is also ohmic resistance between that ground pin and the receptacle. And if that gets too sloppy, typically about 4 to 8 ounces or so, you're going to have a lot of resistance in there, reducing the effectiveness of the ground. And then lastly, other than when the device first comes in, you can get rid of tools. I don't know how many, you guys are still doing it for the most part. Leakage currents, a lot of people are. But it's just become such a mainstay of our profession. It's like trying to get people to quit using the QWERTY keyboard. So I'm sure there's going to be a lot of people, I even heard from some of the ISOs, corporate policy, some of the ISOs are doing it because it becomes so tightly coupled with safety. So if you say, I'm not gonna do it anymore, there's sales benefit. It's sell safety. Like, you can sell that functioning practically, especially with all the stuff you guys have to do. You've got thousands of devices. You add up the time it's taking to do these tests. You push it on your ship.
Typically, what I always do is it as plan. Well, plan ain't doing it, so that means nobody. And I've seen receptacles bad.
What kind of, you know, my things are being renovated all the time. So it might have been good at one time. You start renovating things, probably get sloppy, they get used. So it kind of, the insult to your efforts on verifying around configuring the device, gets plugged into a sloppy. Like you said, not your responsibility, like you said, they don't. Nothing you should, just being mindful that you can.
So what's our takeaway from this NFPA 99 versus manufacturers who are saying like fusion pump manufacturers? You've got to do all, want you to perform safety tests, they want you to do leakage.
Now, manufacturers still have to embrace this stuff. Maybe they've gotten rid of the requirements routinely. They still have it in there that maybe an okay thing to do, reasonable thing to do when you first inspect the device, or if you're doing some major repairs related to the inside of the device, check it again, but it doesn't need to be done periodically. Even if the manufacturer says you got to do it periodically, you're probably still coming from this reason. Or if it's something that they want to sell in the name of safety, to charge you more money to do a mask. I mean, you can't really ultimately debate the technical realities of these concepts. You know, it's just like, it's not your opinion.
So you can effectively go from the ground point on the back of the equipment to the actual second receptacle on your ground. And then you're checking the receptacle.
And then you just look out, look at the receptacle is probably the physical.
Yeah.
Go to an ICU, they're not gonna give you the ICU bed. They're gonna keep it open all the time. So I would just say that if I had a point. And like you further said, well, my power cord is rolled up, plugged on the wall, the receptacle is on the wall. And there's no way you're going to have any degradation of the cord itself. Right.
You've got so many more important things you guys can be doing. I mean, make sure the machine works, cell tests work, you got the mechanical integrity stuff, be shredded. That kind of stuff is important, but a lot of these chasing leakage currents, again, they're for years, and you got to be ready to take a stand sometimes. I was at 3 different hospital systems right there, I was at literally because all this stuff. The very first one, if I got a second, the very first one, the very first hospital used to be a NFPA requirement in the ER, monthly conductive floor test. Like the old guys remember that. Again, I would go around the meter, walk around the wall, measure the resistance of the floor. This was a electrical anesthetic agent. This is like 70. So how to do it? Well, I got there, and the maintenance guys, the facilities guys were doing it straight. They had binders of monthly conductive floor tests. That's all of me taking care of the equipment up there. I'll go here, you don't bastard, go there. Take it. Well, I got there for the first couple of months I'm doing this. What the mindless ass stupid day is this? So I just said, I'm doing this. I had more thing to do, you know. I was doing a machine ESU attention. So I just quit doing it. After a year or so, maybe the joint commission came in, they came to serve everything down, the administrator, my boss. I said, well, we used to do it, but we don't anymore. Oh, my boss, the administrator, called me in the office and he, how the hell do you think you like just sense? You know, I'm thinking of this technically, and there's no point on aesthetic. It took a half a damn day to go. I mean, I had averages and all this 3 feet apart, you know, and so we got rid of that. Oh, God. So, yeah, you run into some pushback, clearly, especially if people are still so tightly coupled with safety. If they still think like the leakage currents are going to prevent people from getting electrocuted, you'll feel that. In fact, when I left the hospital, 40 some years, the first time in my entire life I did like a sound. Swimming upstream, he's buried, they're just coming at you, I mean, just, chewing on it, and, God, liberating, you have to fight reality.
All the ORs have line limb monitor built into the room, which, if you elaborate on that, because other places, for a while, man, we have to go out, chase a extension cord out to a hall somewhere, so that you can even perform the test for leakage currents.
Yeah, and that's,
There's no reason to do a leakage current test in an OR. The whole room is on a limb.
yeah, the reason the limbs are there is that it's what we call a predictive monitor. It's a real funky marijuana concept. Oh, yeah, okay, and but it's a, so if you see 2 milliamps on a limb, it's not a current that is flowing anywhere in the system. It's a predictive current that would flow if you had a line of fall. So it's a measure of how good the isolation is in the system. And the isolation is all based on that parasitic capacitance between line 1 and ground, line 2 and ground. So if your isolation transformer is, half a block away, you've got a whole lot of capacitance. So you're going to have a much larger reading as a result of that straight capacitance, degrading the isolation. Theoretically, it should be 0. So when the limb goes off, it becomes something that will maybe last 1 minute that has a high leakage and a high straight capacitance causes. It's not even a current that's flowing yet. So it's a current that would flow if you had a line to ground fault. So if you put you connected your multimeter between L1 and ground, for example, in very low resistance, you probably read about the same current that you're reading on the limb. So it's a goofy concept. It's one that's got us buffalo in that industry that Dr. Noble mentioned earlier. That whole transformer industry, they were pushing this stuff big time. And the isolated power made sense when you had flammable anesthetics. That's when we had to go explosion-proof receptacles with ether, your gas, what you're for. And so if you accidentally pull the plug on the wall, you got a spark. You blow up the room. That's when the receptacles fire off. They also, because of the sparks, they had to conduct this force. That's how you can force to dissipate the static. So you can see the buoys and little conductive strips of the buoys, the casters were conductive, rubber, trimmings had conductive rubber, blood pressure cuffs conductive rubber. It's conductive to drain it. So you needed a conductive floor to drain that static. And so that's what, so we put the isolated power in there because we had a grounded floor. So the isolation power was necessary. Shocks from the isolated grounded floor. So to verify, make things safer, that's what they're doing. Just
So the limb monitors, done, make commercial safety not relevant because you've got a limb doing that job? Or is it just a BS thing that they, some code guy put up?
no, what's kind of always fascinated me was the BS part was the nature of the alarm. When the limb goes off, you think the whole damn building's going to fall off. It's a noxious, annoying, attention-getting alarm, which, like you want in an airplane, when you lose engine power, pull up, the claxons go off, yeah, I want to get your attention. This event didn't even happen yet. So the safety relevant event hasn't even happened because the limb just simply is telling you what current would flow if I had a limb. So it's a really bizarre, abstract concept, an instrument. And it's not a common for decades. I had buses, they're noise. You get called there, plug something in the line, and it's fine. It's a predictive meter. I've never, when you want to predict something. So again, it's a current that isn't even flowing yet. You think of that. What good is that to you? Like something that's theoretical, instantaneous voltage measure and stuff. That's what you guys got your job cut out for it. I'm telling you, a lot of this stuff that simply hasn't changed. If you take out the establishment, you take out your box, you're not doing this stuff anymore. If they didn't get it, they don't understand it. They're just going to tell you to keep doing what you're doing. And for me, when I have my text, it was an insult. The skills are way too high. Because this all thing you're And you do this pointless move now. You know, you got very skilled, seasoned people here that can really do some powerful stuff, and you got them chasing these dumbass, wasting their slot. And you come back and back it up. Of course, most of the people I'm trying to explain this to, they want you to talk. Me and Larry kept talking, he doesn't understand anything, so that's where you're kind of doing.
So what happened to you at that one job?
One guy put it on, yeah, I didn't get 5 days back. My second job, the joint commission inspection, we would be doing our post program, and one of the things on the tape of the program was operating tape. Yeah, we're supposed to get to it, we didn't, we just pull on the very cool. Surveyors came in, all the inspection, 4:30 of them, one day, I got to talk to my boss, frantic, and let me need to see all your operating table, PM records from the surveyor. This job, we're not doing anything on our OR tables. You don't understand, I need all your records on the OR table off my desk tomorrow morning. We don't do OR tables, I don't have anything. So do whatever you got to do, have them on my desk. You got to tell them to make them. I had that whole thing. Of course, I went into just combat mode. I got called the next morning, 7 o'clock in the morning. God damn it, I have a record. John, you don't have them. Well, get away from the weekend as soon as you can. Come to find out, the OR had those things on contract. So they had they invented those OR tables had all the records. And I thought, man, you know, I was good with it. I was that far. Push comes to shove, I'm over. Fortunately, they didn't have to do that. Well, the manufacturer had it, the OR manager, they had all the damn records in the OR. We just, I didn't. But here was all stuff was already covered, and he was effectively telling me that. He didn't tell me what I was telling him, he said, do whatever you gotta do. Well, we don't have to do whatever you gotta do.